Hey guys, for this video, the only objective is to look at some of inertia worked examples. Cool. So first example I've got here says find the moment of inertia of a massless rod with 1 point mass 2 kilograms lying 20 centimeters from the axis of rotation and another 1.5 kilograms lying 40 centimeters from the axis. If the first mass has a velocity of 2 meters per second, find the rotational kinetic energy of the rod. Right, so effectively two questions in one, and you'll see that while it's not so complicated, it does actually take quite a bit of work. So what we're going to do is first draw a nice diagram of our rod. Right, so we've got 1 point mass here that lies about 20 centimeters from that axis, and the other one here which lies 40 centimeters from the axis. This one's 2 kilograms and this one's 1.5 kilograms. Okay, now we can just write down the formula from our formula sheet, which says the moment of inertia equals the sum of all the point masses times their distance from the axis of rotation squared. So we've got one that is 2 kilograms and it's 20 centimeters from the axis of rotation, and the other which is 1.5 and it is 40 centimeters from the axis of rotation. It doesn't matter that they're differing directions from the axis of rotation. We don't really need to find one as minus because we're just going to be squaring them anyway, so that doesn't really matter. And if you put that all into your calculator, you end up with the moment of inertia being 0.32 kilograms per meter squared. Right, so quite a simple start. What we're going to do now is try to figure out that rotational kinetic energy if the velocity is 2 meters per second. Cool, so we have the formula, K equals half mv squared. And what I'm going to do is look at just the point mass that they've given us. So they've told us that this point mass is moving at 2 meters per second squared. So I'm going to put some eyes in there just to show that it's a point mass. And we've actually got all these values. It weighs 2 kilograms and its velocity is 2 meters per second. Cool. So put that in your calculator, work it out in your head. It's actually 4 joules of translational kinetic energy. So I'm just going to move onto a new page. Right, so we figured out that point mass has 4 joules of kinetic energy. We also know, we also have this formula, which we saw in a previous video. This is r squared omega squared, because we can just sub in that formula that we've got over there into our kinetic energy. So this is an r, and we can now sub in what we know. The radius, if you'll recall, it was 20 centimeters from that axis of rotation, and omega squared is what we're trying to find out, and I'll show you why in a second. If we do some rearranging, we end up with that omega equals 10 radians per second squared. Now to find the entire rotational kinetic energy of the rod, we just use the formula of our formula sheet, which says that rotational kinetic energy equals half times the moment of inertia times omega squared. And we have all those things, we've figured them out. Put that all in your calculator, you end up with the rotational energy being 1.6 joules. Rotational kinetic energy being 1.6 joules. So that's how we use those formulas. That's most of them are off the formula sheet. Don't really need to remember them. We're now going to look at a slightly more complicated example right here. So it says find the moment of inertia for a straight rod of mass m and length l. The axis of rotation is through its center. So I've drawn it here. What we're going to look at is an infinitesimally small point dr. That's how far it is from the center, dr, and it's got mass dm. Right, so I've written down the formula for a moment of inertia of an object made up of an infinite number of point masses. So you can see why it's going to be a bit more complicated, because we can't integrate this yet, because we've got r squared in terms of dm. So what we need to do is figure out how we can change one of these to suit our equation. And what we need to know is that the mass of this small point dr we can actually find by the density of the rod times by the length dr. So the mass dm is equal to the density of the rod times the length of dr, that infinitesimally small point, right? So already we're starting to get rid of this dm. Now the density of a rod is just mass over volume, but in this case we're sort of only assuming it's two-dimensional, so it would just be mass over length. Right, now we can sub that across in here. Cool, and now it just becomes quite a simple integration. So the first part's complicated, the next part's quite simple. We can take that m over l out, and we end up with r cubed over 3 from, well, if it's going through the center, if it's rotating through the center, this point here is l over 2, and this point here is minus l over 2. Right, so we're integrating from minus l over 2 to l over 2. Right, so we end up with m over, we can take that 3 out, of l cubed over 8 minus l cubed over 8. Just do some fraction work and you'll end up with that. Actually, the inertia of the rod is actually 1 over 12 ml squared. Right, so that's quite rare that you'll actually see a question of that difficulty. Often they'll give you the moment of inertia for different shapes, but if it does come up, we now know what we need to do. So that concludes this lesson. Thanks, guys.